system, we can consider that the robotic system basically it performs three actions. It senses, okay, this is what is related to perception. It then processes the information that it receives from its sensors. Okay, this is the, let's say, the thinking part. And finally, it will make some kind of actuation, maybe moving from one location to another, or moving the actuators of a robotic arm, or if it is a drone, it's going to fly, and so on. So what ROS actually provides to you, it provides very nice abstraction to the perception, it provides very nice abstraction to the low-level drivers and hardware. So you don't need to know about which hardware you are going to work with, because ROS is going to provide some kind of interfaces that will allow you to easily manipulate any kind of sensors and any kind of actuator. Now, for example, if you want to use a camera with ROS, you don't need to know, okay, which camera brand I'm going to use, how should I bring the signal from the camera, or how should I capture the image from the camera, or if you have a laser scanner, you don't need to worry about this. All you need to do is just to know how you can bring this information from ROS. So usually ROS provides all the interfaces and provide all the low-level software APIs to extract information from the hardware. And then as a software developer, you just need to focus only on the information that you can take from ROS, which we call ROS topics, for example, or the information that is flowing around through the ROS messages. Same thing for actuation. If you want to make the robot move, you just need to publish some kind of message. And the good thing in ROS that it provides some kind of standard APIs. Okay, if you want to make the robot move, you have like the twist message that allow you to send twist commands either to a robotic arm, or you send twist command to a ground robot, or you send twist command to a flying robot, or anything else. So as a software developer, all what you are going to focus on is the thinking part, is the processing part of the information. How are you going to transform the data coming from the perception modules, okay, into the actuation modules? So you can focus on this, and this is what I actually wanted to have. I didn't want to bother myself about how to collect data from the sensors or how to send information to the actuators, but we want to focus on the high-level APIs. This is just one perspective of the benefits that you can use of using ROS. Of course, there should be so many others, but it really makes a lot of simplification to the process of the software development. Now, seeing the impact of ROS, this is one snapshot taken from the metrics report of Open Robotics in July 2019. So you can see the statistics over the month of July. It's a huge number of users all over the world, with a big concentration in China, in the United States, Japan, Germany, South Korea. And basically there are 2 million page views per month in the month of July 2019, and up to more than 120,000 new users every month coming into the ROS world. So this actually shows the significant impact into the robotics scientific community. I mean, now everyone who would like to learn about robotics, the first thing maybe he need to start learning is how to develop software with ROS. You can see also the increase of the number of users. Now here also this is taken from the metrics.ros.org. You can find it over there. And you can see here the blue line, the increase of the number of users every year. From 2011, basically the start of ROS. Basically I've started to use ROS from this year until 2020. And you can see here there are some kind of few jumps. I guess that this is during the ROSCON period. I mean, ROSCON period is around end of October every year. Now imagine that you would like to develop a self-driving car. Okay, this is something possible. We have already real products about self-driving cars, and basically they also use ROS. But for this, you will need several modules. You need a perception module, okay? How to collect information from different cameras, how to collect information from laser scanners, from LiDAR sensors, okay? You need also to process this information. Okay, you need also different libraries and framework, for example, for computer vision or for matrix computation, or you need some kind of predefined mathematical models. You need also a way to communicate between the different sensor and hardware. You need also some artificial intelligence and machine learning strategies in order to be able to process the information and transform them into appropriate action. So if you don't have ROS, you have to bring up all these different tools together. But the great benefit of ROS that it provides you a standard way. It provides you one ecosystem, a unified ecosystem, a standard ecosystem with all the functionalities that you need to develop your software. So it will eliminate all the hurdle and the headache of trying to find out what kind of tools and software you have to use. And if you work with open source, everybody knows the problems of compatibility issues, the different issues of versions and stuff like this. So ROS makes everything compact, bringing them into one ecosystem and provide reusable components that can be easily integrated in any kind of application. Okay, so this clearly shows the great impact and the benefit that ROS bring to the software development of robotic platforms. Without this, it's going to be pretty much difficult. I mean, in the area prior to ROS, most of the software developers of robots, everyone would have its own proprietary software, and there is no compatibility. So if you want to make one robot work with another, it's going to be very difficult because they use different software abstraction, they use different software APIs, and they use even different type of communication protocols. Now everything with ROS becomes unified and standardized. So we can consider ROS as the de facto standard for the robotics software development. So what is ROS now? ROS, basically, we can consider ROS as a middleware, okay? As a middleware that provides high-level abstraction between low-level hardware and drivers and high-level software APIs. So in this slide, I show the different distributions of ROS from maybe when it was a small project in 2007 from Willow Garage and Stanford University AI Lab. And then, let's say the first release was in March 2010 with the box version. So usually with ROS, we have different versions, and every time we use the letter B, the letter C, the letter D as first letter to design the name of the version. Okay, I have been using ROS from the electric version, and now we have the latest version that was released for ROS 1 is the melodic version, released in 2018. And basically, some of the versions, they have long-term support. So that's why they are more popular than others. I'm going to show you now which versions have been pretty much used over the time. You can see here the evolution of usage of the different ROS versions. So for example, you can see from 2014, okay, we have the ROS Indigo version. This is the long time support. Is it possible to mute there is a background noise? Yeah, okay. So you can see ROS Indigo, this is one of the long time support version. It has taken, this is in the blue color here. It has been very active until around 2018. And then there is the ROS Kinetic, that is another LTS version. So you can see, for example, for Jade, it's not a long-time support, a Lunar long-time support. It's not pretty popular among the ROS users. ROS users basically would like to use the long-time support versions like the Kinetic. Kinetic is still being actively used until now, although it was released in 2016, but still it's being used around by 50% of the ROS users. And also we have Melodic that starts also to take to have some impact in the last 2 years, 2019 and 2020. 2020. So now comparing the usage of ROS and ROS2, you can see even now until March 2020, most of the people are still using ROS1 version, despite that ROS2 version was already released in 2017 the first time with the Ardent version. Okay, here. The issue is that ROS2 is still under development, and I think the future is going to be for ROS2 because it is addressing a lot of issues and a lot of problems that ROS1 users have faced, and I'm going to explain the difference between both versions. But still, until now, most of the users are focusing on ROS1, only very little. Okay, so the last version of ROS2 is Eloquent and is going to be released in next May 2020. The current version is Dashing now, currently available. Okay. So let's look at the ROS architecture. Basically, ROS, it is composed of the concept of nodes. And nodes, basically, they are processes running into a computer. Okay, so you can define one program here, you can call it a node, another program, it's called a node. And these nodes are going to register themselves using the ROS master. The ROS master, this is the core node of a ROS ecosystem. Now, in ROS1, in order to be able to run ROS, first of all, you need to run the ROS master node. And finally, all these nodes will be able to communicate with each other after registering themselves into the ROS master node. And of course, this makes one of the problems that it is prone to the single point of failure, because if the ROS master is crashing, so your total application, all the other nodes will be crashing as well. And then ROS defines different client libraries, both in the Python programming language and in C++ programming language. So these are the two main programming languages. Also, there are some client library in Java, but they are less popular. And it uses TCP and UDP for inter-process communication. And basically, ROS1 was developed for Linux operating system, although there are some like experimental version for Mac and Windows, but they are not of pretty much use in what concerns ROS1. So this is the the architecture of ROS. Now, let's introduce the main concept of ROS. Usually when you want to start a ROS application, first of all, you need to start the ROS core, which is the ROS master. And then you can start different nodes. Now, for example, we are going to start one node that is our robot here. And another node here for the teleoperation. So the first thing, these nodes are going to contact the ROS master to advertise themselves. So this one is going to say, okay, I am a robot. I'm called TurtleSim. I'm subscriber to velocity message. So if there is any velocity message, you can send on the following topic over the following message. And same thing for this teleoperation node is going to advertise itself, giving its name. It's a publisher of velocity command, okay? And this is the type of message. And then this ROS core is going to make the connection between these two different nodes. So finally, these two different nodes will be able to communicate directly either using TCP or UDP. So this is the whole life cycle of how to run a ROS, let's say a ROS program here. Let me show you a demonstration. Maybe we have some people that are new to ROS. Okay, so basically the first thing you need to do is to run a ROS core. This is the ROS master. Without running the ROS master, you cannot run any application. And then you can write your different nodes. So a node simply is a program. It's a process that will be running. Now this is the process running the robot. And here we have a simple TurtleSim. This is the best tool to start learning about ROS. Very simple and makes a lot of abstraction, but the same way can be applied to any real robot. And then you open the teleop here, So this is another node that is the teleop, from where you can send commands to make this robot move. Okay? And now, if you want to check the number of the list of different programs that are running into a ROS ecosystem, you can use some very simple terminal commands like ROS node list over here. Okay, sorry. Okay, so ROS node list is going to give you the number of the different processes that are running currently into the ROS ecosystem. You can check what are the different topics through which you can send messages. Now, for example, you want to send a velocity message, so you know that the velocity message is defined by the following topic name. And finally, you can also monitor the messages running through a topic. Now, if we make the robot move, you can see that we can see the messages that are running. And this is also a very simple example on TurtleSim, but the same process can be applied on any kind of robot. And this is actually the universality of using ROS, is that you can use it with any kind of robot in the same way. The same way that you use TurtleSim, you can use it for any kind of robot, whatever it is, a robotic arm, or if it is a drone, UAV, or anything else. And finally, you have different programming APIs, like for example, you can define a Python program or C++ program to run your node. Of course, here Python is pretty much simple, much simpler than the C++. But of course, C++ might provide better performance if you need some kind of real-time execution performance. Now, in terms of the, let's say, communication paradigm, in the ROS operating system, we have three main communication approaches. We have the publisher-subscriber, which is the most common. So basically, you have some nodes that will work as publisher and some other nodes that will work as subscriber. Okay, so let's imagine that you have a laser scanner like this, and you have a node that would like to avoid obstacles. So what you will do, you will just subscribe to the information coming from the laser scanner. And the laser scanner is going to provide you all the information about the obstacles that you have. It's going to provide you an array of distances, and these distances will provide you what is the obstacle in every orientation. Okay, so the subscriber can use this information and develop algorithm to avoid obstacles. Okay, and this can be applied with any other kind of device. Instead of having a laser scanner, you can have a camera, for example, or you can have any other kind of sensor, ultrasonic sensor, or any other kind of sensor. And the publisher, okay, so imagine that now you know all your different obstacles. In this case, you can publish a command that is the velocity command to tell the robot to move to a certain location and to avoid the obstacles. So basically, the publisher and subscriber, this is the most common model, communication model between the different nodes into ROS ecosystem. You have also ROS services, and here you will have a synchronous communication between a client and the server. So one server is going to provide some services, and the client will need to communicate to send a request and receive a response back. So this is different from the publisher-subscriber, because here it's one-way communication. It goes always from the publisher to the subscriber. Anything that you have new, you are going to send the new information to the subscriber without having an explicit request. Otherwise, in the services, the client is going to send the request, receive a response, and then the communication is going to end. If you want to have another information, you have to send another request, and then you will get back another response. So this communication paradigm is synchronous. Okay? So the client, when it sends a request, is going to wait until the response. So it's going to be blocked until the response is coming. So ROS community has found another way of communication that is called the action leap. And action leap is completely asynchronous. It's like you have also a client and a server, and the difference here is that the client will send a request, and then it can do anything else. It will not be blocked until the response is coming, because sometimes the response is going to take time. Okay, and whenever there are some intermediate states, so the server is going to inform the client, okay, I just achieved, for example, maybe 20% of the work, 30% of the work, or 90% of the work. And finally, when the work is completed, the server is going to say, okay, the work is completely done. An example of Action Leap is the move base, that is the navigation stack of ROS. So basically, the navigation stack, you send the client, any node in your ecosystem will send a goal location. It will send a goal location to the move base server. So during this time, the move base server is going to execute the local path planner and the global path planner to make the robot move. And in the meanwhile, the client can do other things, for example, making other computation or getting some sensor information and so on. In the meanwhile, the move base is going to send to update the client with the state of the mission, what is the current location of the robot after moving, and finally, when it reaches the location, the target location, it is going to say, okay, the mission is completed, or maybe if the destination is not reachable, it will say unable to reach the destination. So move base, basically, this is a popular example of using Action Leap in ROS. So these are the three main communication paradigm: publisher, subscriber, ROS services, and Action Leap. Another very important thing in ROS is that it dramatically simplifies the navigation. I mean, navigation is very, very complex. You need to build a map, you need to navigate inside the map, you need to be able to specify the locations where you want to move, you need to avoid obstacles. This is one of the most difficult operations that someone has to do with a robot. And fortunately, ROS provide all the needed abstractions and APIs for easily navigating inside any environment. It provides some packages for building the map using SLAM, and provides some other packages for making the navigation using a robot. And basically, the words that are implemented, they are dated from 2000, from the thesis of Sebastian Thorne about probabilistic robotics. It's very nice work from 2000. Also, some other works related to the local path planner, the DWA algorithm. And now all these different techniques are implemented into ROS and comes working out of the box with just need for small configurations only. Okay, so something to know is that ROS provides two types of path planners. We have the global path planner, which is responsible for providing the path from the initial location to the target location. So it's going to make a path planning algorithm, like, for example, A-star or Dijkstra. And you have the local path planner that is responsible of executing the path that is found by the global path planner. Okay, we have released a book that is called Robot Path Planning and Cooperation, in which we have developed different path planning techniques, and we have also demonstrated how we can implement new path planners as a global path planner into ROS. So I consider that the navigation stack and the TF package is one of the most popular packages in robot operating system that makes it really easy for anyone to develop navigation algorithms for mobile robots. Okay, so far I have presented the benefits of the robot operating system, but still it has some limitations. So the limitations of ROS, that it is basically designed for the single robot case. It was not designed for the swarm or the communication of robots. That's why if you want to do multi-robot cooperation with ROS, either you need to develop your own packages for multi-robot communication, or there are some contributed packages that are provided by some researchers. But there is nothing native that will allow the robots to communicate between each other using robot operating system. Another issue with ROS is that it is not real-time. It is based on UDP and TCP, so from processes perspective, all the processes would have the same priority, and maybe we need to differentiate between the priority we need to differentiate between the priority of the processes running into a robot, because sometimes you may have processes that have higher priority. For example, if you have a process to avoid obstacle, this is more important than, for example, another process for example, moving a robot or something else. But in ROS, there is no way to say that this process or this node has higher priority than the other. Another thing is that ROS requires a very reliable network, because basically ROS will be composed of several nodes, maybe tens of nodes, and all these nodes will communicate between each other, and every node is going to consume a bandwidth. So you will assume that you have a high and reliable bandwidth connection, network connection between the different processes running inside the robot. And this is something maybe not easy to provide every time. And another thing is the problem of ROS master. And we have the problem of the single point of failure. So that's why the ROS community, I think maybe in 2013, 2014, they started to think about another alternative of the current ROS operating system, and they started to design ROS 2. And the idea of ROS 2 here is, first of all, to get rid of the ROS master and to change it with a more standard way of the communication between processes. So the processes will be standalone. They don't have to be registered with a central node that is the ROS core or the ROS master. And for this, they have used the standard data distribution DDS here for the communication between the different nodes. And different changes were done for the client libraries. So still we have the Python client API and the C++ client API. Okay, other changes is that ROS 2 was not only designed to the Linux operating system, but also it was designed to be cross-platform for Linux, Windows, and Mac OS. So several of the limitations of ROS were addressed in the design of ROS 2, which is currently being developed by the ROS 2 community. Okay, so ROS 2 actually target to use a swarm of robots instead of the single robot case. It also implements quality of service and real-time guarantees. So there are ways to define quality of service profiles between the processes, so you can give a priority to one process over the other. It is also designed to be cross-platform, and the objective is to facilitate the transition from prototyping to production. Now, when it comes to designing what kind of middleware, so in ROS 1, basically it has its own proper middleware that is based on ROS TCP and ROS UDP. So one alternative was try to improve the legacy protocols, okay, to make them real-time and so on. But at the end, the second strategy was to build a new or to use an existing solution, like for example ZeroMQ or protocol buffers from Google, ZeroConf or DDS from RTI. So finally, DDS was actually selected to be the middleware. Instead of using TCP ROS or UDP ROS, DDS is going to replace it for the communication between the processes, and this is going to give much more scalability and flexibility, real-time performance, quality of service, and so on. So what is DDS? Is the data distribution service. It's already an industry standard communication system, okay? It's an old system. It's independent from ROS, but it was later on integrated into ROS, and I'm going to explain the why. And it is designed by the Object Management Group. It is a data-centric publish-subscribe system. So it basically shares some common features with ROS in the sense that it provides publisher and subscribe mechanisms. It provides real-time machine-to-machine communication, and it is used in different application contexts, like the financial trading, the air traffic control, smart grid management, big data, and IoT applications. Yeah, and it's pretty much all started in 2001 by RTI in the US and Thales Group in France. So why DDS? This is a presentation that I have found on YouTube from Rick Warren, okay, from RTI, which is the main developer of data distribution system. And looking at how DDS work, or the concept and terminologies, so let's look at the different concepts. In DDS, they define the kind of domain, okay? So the domain, this is like, we differentiate between different domains or different subsystems and or of a particular application. Now, for example, in our case, the domain is going to be ROS. And they define similar concept to ROS like the topic. And the topic here is a group of similar things. And below topics in the hierarchy, you have instance. And it's defined as individual changing things. And besides the instance, you have a sample, which is a snapshot of the instance at a point of time. Now, if we want to map these different terminologies and concepts to ROS, so topic is going to be the same as a topic in ROS. The domain here will be the ROS ecosystem. The instance will be the message, okay? So an instance here will be the message that is going to bring a data between ROS processes. And the sample, okay, it will be an individual message, okay, that is sent between two processes. So the same terminology was pretty much compatible with the ROS terminology, and I think this is one of the reasons why DDS was adopted for ROS2 as a middleware for communication. And you have data writer and data reader. So basically here it's pretty much intuitive. Data writer are for publishers and data reader are for the subscribers. So there is pretty much similarity between the design concept of the data distribution service and also the different concepts for the inter-process communication in ROS, or inter-process communication in ROS. Okay, so DDS finally was chosen. It simplifies a lot the network programming, and it provides inherent publisher-subscriber patterns that are very suitable to ROS, and it shares several similar features with ROS, like topics, creating topics, publishing messages, subscribing to messages, and so on. And it also defines some discovery protocols, because now you don't have a ROS master, so you must have kind of protocol to be able to discover what are the different nodes running in your ecosystem. And it defines messages, so ROS2 messages maintain the same message definition as ROS1, but they need to be converted into a message format that is understood by the DDS transport layer. And this is what we call serialization. Okay, and it has been proven that the serialization is not costly in terms of execution time. And the good thing about DDS, you are not tied to use DDS implementation from one particular vendor. So you can use the DDS implementation from RTI or from OpenSlice DDS or from any other DDS provider. So even in ROS2 now, you can choose which DDS distribution. There are several DDS distributions that are compatible with ROS2 and that you can choose among them. Okay, this is the current state of ROS2. It started from 2017 with the Ardent app alone, and now in November, November 2019, we have the Illusoar. So let me finalize my presentation with providing different contributions to ROS. Dr. Ibrahim, do I still have time? Maybe 10-15 minutes? Okay. Yes, I will need maybe 10 minutes, yes, to finish. Okay, so we have been using ROS in both education and research. So in terms of education, using ROS was providing as a means to teach ROS for computer science students. And this is not actually very easy, because usually computer scientists, software engineers, as already mentioned in the beginning, they don't have like the sufficient background like electrical engineering and computer engineering about the hardware level. So they want just to focus on the high-level software development. So ROS actually was very perfect framework. This is one application developed by the students for Turtlebot 2 robot, for example, to go to the cafe, bring a coffee, and bring it back to the office here. Okay, this actually allows the students, even from different backgrounds, with software background, software engineering background, to learn about robotics and to develop their own application quite easily. Yes. This is also some other applications that we have developed with the students to emulate a radar system, okay? To emulate a radar system using a laser rangefinder. And the idea here was actually to detect the speed of a car moving in front of a laser scanner by implementing some kind of speed estimation and making an alarm if the speed was exceeding a certain threshold. So this was done by software engineering and computer science students. It also to introduce students to the world of drones quite easily, because as I mentioned to you now, we would like just, if we want to make the drone move, we want just to send a takeoff command or to send a velocity command, and the robot operating system provides the required, provide different means in order to make these things pretty much simple. This is the AR drone simulator with ROS. Okay, and another thing that we have done also in collaboration with Gaitec company, this is our partner in China. I have been R&D consultant with Gaitec, and we have developed for them this website that is called Gaitec Edu. It contains a lot of tutorials. I have developed a lot of tutorials here. It's a good place to learn about ROS. If you want to learn about navigation or basic concepts, so you can find them here in Turtlebot tutorials. We have also developed a robotic platform that is called the RIA E100. And this platform is designed specifically for research and education. It has a Core i5 computer here. It has a laser of 360 degrees. It has an RGB camera. And you can also extend it with the GPUs. You can extend it with the robotic arm. It's pretty much complete tool for education and research. And we have a lot of tutorials and resources available that you can find them on edu.gaitec.hk. We have also a bigger platform. This is for research and education. There is another platform that is called the RIA R100, which is bigger in size and for heavier payloads. Okay, another thing that I really enjoy to teach ROS and to share the ROS with others. So I developed different courses on Udemy, ROS for Beginners, Basics, Motion, and OpenCV, and ROS for Beginners 2, which focuses on localization, navigation, and SLAM. I have also another course about ROS 2, the basic concepts of ROS 2, and one other course about programming in Java. So, alhamdulillah, the courses actually are best sellers now on Udemy. Basically, in terms of content, they were really designed to introduce all the needed concept for robot operating system. And usually I take the benefit from the summer to add more content to my courses. So this course, I developed this one in the previous summer. Now it contains everything related to map-based navigation, but still I need to add some content more to the map-based navigation and also to the reactive navigation. But the current content already provide complete introduction to this, to the important concept for someone, because learning ROS takes time. And there are a lot of ROS courses, a lot of documentation in ROS Wiki, but for someone, a beginner, he's going to be pretty much easily lost into all the different documentation. So here, based on the previous experience of teaching ROS to the students, I have just tried to put all the different resources into one place with live demonstrations. Okay, some of the videos may be old here, but some of the videos are are very recent also. This one is a recent course just for the previous summer. For the ROS2, basically I did this 2 years ago, but it will require that I have to update because I did this when they have released the bouncy version. And at that time, ROS2 was not as mature as today. But probably in the summer, I'm going to continue this for making it more comprehensive. But this course just provides an introduction to the new concepts in ROS2 as compared to ROS1. Another thing also they have done for the research community is the Springer books. I have now 5 volumes of robot operating system. This series started from 2016. Now we have 5 volumes. The 5th volume is going to be released maybe in 2 or 3 months. And we are accepting chapters for volume number 6. And these books are one of the most downloaded on Springer. So for example, for volume 1, it has been downloaded more than 212,000 times by readers. So if you are interested to submit, I will be glad to receive your submission. You can submit an abstract as soon as you can. And basically the deadline to submit the chapter, it is May 30, but probably due to the COVID-19 issues and stuff like this, maybe I will make an extension for a couple of weeks. Okay, so also I have developed a tutorial, a unique tutorial about how to write a global path planner for ROS. And this was one of the most difficult contributions I have done. It was not easy because writing a plugin for ROS is very, very complicated. And at that time, there is no tutorial that tells you how to do this for Path Planner. So after a lot of search, I have tried to put everything into one place. And now, just by following this tutorial, you'll be able to write your own global Path Planner plugin. For example, if you have a new Path Planner that maybe outperform A-star or Dijkstra, you can try to implement it and test it as a global Path Planner in ROS. Some other works that we have done is developing service robot with ROS. And here we have tried to develop web services interfaces to be able to communicate a mobile application with ROS. So the idea here is that we have used ROS Java inside the robot to develop web services inside the robot here. And then using a mobile application on Android, we can invoke the web services in Java, and then they will translate these web services request into ROS command to make the robot move and execute a particular action. So here in this demonstration, it was just to make pick and place using a robotic arm and submit the document to another office. So we have developed a complete software abstractions to be able to send the web service request to ROS. I think there is an issue with this slide in particular. Okay, another contribution was also to make multi-robot task allocation, and this is one of the limitations I have talked about ROS, that it doesn't provide any native means to make the robot communicate between each other. Maybe you can do all the robot into one ROS master, but this is not very scalable. So we have developed a complete architecture for multi-robot allocation, which we have called Chorus. And it has different modules. It was built in C++, and it defined a server agent and an operator agent in every robot, and this will allow the robots to exchange messages over a local area network. But you know, at that time, I started to think, why should I be confined to developing application for robots just in a local area network? Because in order to make this robot communicate between each other, I had to work into using one local area network with inside an indoor environment. But my objective was actually to control the robot anywhere and anytime. So there were some strategies for this. Okay, so when we have been doing the experiments, this is the CCIS map that we have built using a robot. Okay, the first floor in our university, and all the experiments were confined to a very limited space. And my objective was to be able to control the robots anywhere and anytime. There were some kind of solutions like using ROS Bridge But the problem of Ross Bridge is that the server was embedded into the robot itself. Ross Bridge allows you to interact with the robot using web interfaces. And our objective basically is try to move Ross to the cloud. Okay? So, and we want to do this for two objectives. The first objective is to make computation offloading instead of processing everything on the robot or on the drone, which have limited, they have limited energy and processing capabilities. We wanted to offload the computation into the cloud, and also we wanted to be able to control these drones or these robots over the cloud using ROS. So we have, this is the problem with ROS. In ROS, usually you have a ROS master, and every robot needs to run its own ROS master, and then you can have one user that is connected to that ROS master. But if you want to control all these robots at once, that was not possible in this way. So another alternative was to use only one ROS master and connect all the robots to it. But this is also not very scalable from one perspective, and you need to make a lot of work in terms of renaming the topics for the different kind of robots. So this solution, although it's feasible, but it's not practical. Okay, if you want to just plug and play any robot to ROS ecosystem and then allow any user to control the robot anywhere and anytime, this solution was not very practical. So at the end, we have designed a cloud-based system, okay, and we developed a serialization protocol that is called the ROSLink that will allow to have a server into the cloud, and then every robot will have its own ROS, okay, with its own ROS master. And here we will define another layer that is called the ROSLink bridge. What it will do, it will serialize the messages from ROS and send them through the cloud. And this will allow several users to connect to the cloud and be connected to their respective robots. Inshallah, in the next lecture after 2 weeks, I will even show you all the details about this solution. And I can show you live demonstrations. I can even give you access to remotely control your robot from wherever you are through the ROSLink cloud system. So this is the ROSLink basic architecture. You have a robot. This is the hardware of the robot, and on top of it you have ROS. So what we will do, we're going to build the ROSLink bridge, which is another ROS node that will subscribe and publish to all the topics of ROS ecosystem, and then serialize all the messages, send them to a cloud server through the ROSLink proxy. So ROSLink proxy, this is a server here that will receive messages and will forward them to the client. Same thing, the client will have a ROSLink client API that will allow him to receive all the messages about the robots, for example, their states or their locations, and also he can send commands through all the robots to make them move. He can also receive, now we have also implemented video streaming. We can implement video streaming application from the robot to the end user, and we can send command to the user from up to the robot. Okay, this is one of the first applications that we have implemented to control a drone over the internet. Okay, so this is me here in the football field of Princeton University, and having the following mobile application here. I can send a request to the drone, and the drone is going to follow me, okay, by receiving continuous requests from the mobile application about my position. Okay, and we can even visualize the location of the drone on the Google map in real time. This is another demo based on the same system. Sorry, just remove the volume here. That we have developed for Huawei, and we have tested the system on a 5G network. And basically on 5G, it works pretty much fine in terms of video streaming. We are able to receive video streams. This is through the internet, through the 5G network. And we are able even to locate through 5G the location of the robot while it is navigating in the space. So you can be in any country and your robot in any other country, and you can see in real time where the robot is navigating and what the robot is seeing, okay, through the Roslink system. Of course, this solution needs a very good communication bandwidth to be able to have a high quality of service. Look here, we can receive up to 20 frames per second from the robot. And this is feasible because we are in 5G network. But in 4G, usually we can reach 4 frames per second, 5 frames per second. Now, the network technology that is used play an important role about the quality of service of the application. So I will finish with this slide. Another work that we have done with ROS also is the platooning. And the platooning here is that we have autonomous cars, one car that autonomously follow another one. This car is driven manually, and this car will try to maintain a safe distance autonomously, okay, using a camera and a laser scanner. So this work was done in collaboration with Sister Research Center in Portugal, with Enio, our PhD students, and Ricardo Severino also. And we have developed a platooning system. This is also based on ROS, okay, for the demonstration of a platooning system. In this lecture, I will present how to install ROS Neotic on Ubuntu 20.04. Also, I will show you how to create your Catkin workspace and then clone the GIT Hub repository of this course that is compatible with ROS Neotic, compile the ROS project, and finally execute the sample code in C++ and Python. Note that this video just shows the bare instructions. In the future lectures, we will discuss all the concepts in details. So let's see how you can make your workspace up and running. To install ROS, you first need to go to the installation page. Okay, so you can Google this and going to the ROS installation page. And here you will find three different options: ROS Kinetic, ROS Melodic, and ROS Neotic. In this lecture, I'm going to show you how to install ROS Neotic on your Ubuntu operating system. And the advantage of this version is that it has a long time support, an LTS version, and is supported until May 2025. So you need to click on the link and you will be redirected to the installation page. You choose Ubuntu, since we are going to install it in Ubuntu, and then we can install ROS1, okay, by following the different steps, setting up the source list, then setting up the keys, and finally performing the installation from Debian packages. The installation is going to take some time until it completes. After finishing the installation, we need also to source the file setup.bash located in opt/ros/neotic. So here we have installed the Neotic version, which is the latest version of ROS1. Or also we can add the source command into the .bash rc. By doing so, you no longer need to manually source the setup.bash file, and it will be sourced automatically every time you open a new terminal. You can verify that your ROS1 installation is working fine by typing ROS core, and now in this case everything is working as expected. Finishing the installation, you need to set up your environment. And for doing so, you can go to ROS tutorials and then start the first tutorial installing and configuring your ROS workspace. First, you need to make sure that the file setup.bash is already sourced and is already included into the .bash rc file. Then you are ready to create your ROS workspace. So you just need to copy paste these commands: mkdir-p catkin ws src. It's going to create the directory, the workspace directory, and then you make cd the workspace directory, and then you compile it. You compile the directory to create a ROS workspace. It's an empty ROS workspace, and now I'm going to show you how you can put the sample code of this course into your Catkin workspace. To activate your newly created Catkin workspace, you need to source the setup.bash file that is located in the devel folder. of your Catkin workspace. And to do so, you need to add the following command into the .bash rc file, that is source, and then the path to your Catkin workspace. In my case, it is /home/akuba/catkinws devel. This is the location where the setup.bash file that needs to be sourced. Okay, you save, you close, and then you source again the .bash rc for your Catkin workspace to be activated as the default repository. And to verify this, you can just type roscd, and finally you will be redirected to your Catkin workspace. In this course, I'm going to provide you with several demos and examples. And to make your life simple, I'm going to show you how you can download all the code that you will need inside this course. So for doing so, you need to go to the Catkin workspace in the src folder, and then you can go to my GitHub repository by Googling it, and it's Kuba GitHub, and then you have the ROS Essentials CPP. This is the repository that we are going to use in this course, ROS Essentials CPP. So this GitHub repository, it has two branches. The master branch, which is valid for ROS Kinetic and ROS Melodic. So you use the master branch for these two ROS distributions. And if you are working with ROS Neotic, in this case, you have to switch to the other branch, okay, which was specifically developed for the ROS Neotic because there are some differences in OpenCV between ROS Neotic and the previous versions. As ROS Neotic, it uses OpenCV 4, and the previous versions, they use OpenCV 3. And now, inside the src folder of the Catkin workspace, you can type the following command, git clone, and then you use the option -b to specify the required branch. In our case, it's ROS Neotic. And finally, you provide the link to the GitHub repository. Now you have all the files downloaded and available into your Catkin workspace. So you can just make ls to see the ROS Essentials CPP folder. And you can also open the file browser and go into the src folder to find the ROS Essentials CPP package already in your Catkin workspace. After downloading the ROS Essentials CPP package, you need to go to the Catkin workspace directory and compile again the whole workspace using the command catkin make. In principle, if everything is fine, you should not have any error. This is now the compilation result of the ROS Essentials CPP package on a fresh installation of ROS Neotic. And now you are ready to test that the ROS Essentials CPP package installation is correct. So first of all, you can run ROS core, and then you can test two examples, the Torkel and Listener of the demo example provided in the ROS Essentials CPP package. So you can make run ROS Essentials CPP, and here you will find the list of all executable. We are going to select the Torkel node, which is written in C++, and here you can start the Torkel start to publish hello world messages. We're going to explain this in all the details in future lectures, but this is just to make sure that your installation is working fine. And on another terminal, you can also run ROS Essentials CPP listener _ node to make sure that the publisher and subscriber can communicate together using the topics. Okay, so if you have this, it means that everything is fine with your installation of ROS and also the ROS Essentials CPP package. And the last thing to test is that the Python code also can be executed correctly. And for this, we are going to use run ROS Essentials CPP, and then we are going to select listener.py. So you can see here that when making the default installation, Python is not recognized because basically we use Python 3. So you need to install Python 3 package to fix the installation. It's very simple. You just need to do sudo apt install Python 3 so that the Python command will be mapped to Python 3. Okay? So you can see without doing this, we will have an error executing Python code. And now if we type Python, it's going to execute fine. Okay, so we can exit and then try again to run the same Python node using Ross run essential CPP. And let's start the talker.py, which is the Python code for the publisher. And here it's publishing hello world. And then we can do the same for the listener node. This is in C++. Also, it is able to listen the message published by the talker.py. So now we have everything fine with the installation of ROS Neotic in addition to the ROS Essentials CPP package. You are now ready to start learning ROS.